Okay, so now we're in R and we're ready to implement this example of PERT CPM. And here's that same diagram for our activities and each of their precedents, their time, both normal and crash time, and their cost, normal and crash. Let's go ahead and record this information into some data structures in R to kind of record it. So the network characteristics, our nodes are recording everything about the activities. And so I've given our activities names from A through F, the first 6 letters of the alphabet. Then I've got the normal times, the crash, the times when crashed. That's maybe kind of difficult is because we've got the amount of time crashed and the time when crashed. The way the book gives it to you is this is the time when crashed. And so that's how I've recorded it here. And then here's the normal cost for each of the activities and the cost once crashed or fully crashed cost. And I've gone ahead and taken the node names and made them row names for this. And that's going to help us out in how we can kind of refer or call the different entries in this data frame. Okay. Taking the times that are the data that's in here, we can kind of compute some extra columns here. And so the max amount of crash is the normal time minus the fully crashed time. And then the marginal cost, I've put this in an if else, mostly because originally I had some activities that couldn't be crashed. And so then we got some division by 0. And so this sort of protects against division by 0. So just making sure that there's some amount of time that can be crashed. And if so, then it's going to be the cost when crashed minus the normal cost over the max amount of crashing. Okay, and that's going to be the marginal cost per unit time that the activity is crashed. Okay, and then our edges, in contrast to all the other network problems that we've done before, the only thing that the edges record is the relationship between the activities. And so what activity precedes another activity? So A precedes B, A precedes C, B precedes D, and so forth. And then I've got some variables to record the number of nodes and number of edges. So let's go ahead and find that critical path. And so let's just find the total time without crashing any activities. This will be sort of a simple linear program where we only have variables for the start time. So those were the Y's that I was noting on the sheet in the last video. So we're going to create start time variables for each node. And we're going to let these nodes go through the node names. So here we're, instead of indexing with numbers, we're indexing with the actual names of the nodes, which are those letters. It's fine. Got to then be careful and kind of use those names as your indexes for your variables throughout, but it'll work. In this example, when we're just trying to find the critical path, we want to minimize the total time, which is the start time of the final node plus the normal time for that activity. So start time of node F. So node F is sort of our final node, plus in node, here's the way to kind of access the data that's inside that node's data frame. Actually, maybe before we talk about accessing it, let's look at what it looks like. So here's that node's data frame. It's got row names with the node names as actually row names. And then its column names are sort of what we created. And so we can access any entry either by giving row 3, column 4, which is fine, but maybe less readable and understandable to us later on. Or we can refer to it by a row name and a column name, which maybe makes it a little bit more readable. So in this case, we're going to take node F, so the row F, which corresponds to that node and we're going to take its normal time. And so in this case, we're not crashing at all. We're just taking normal time for all the activities. And that's going to be our objective, and we're going to minimize that that essentially end of the project time. And then the only constraints that we're going to have are that we don't start an activity before its predecessors are finished. And so I guess I wrote this kind of the opposite way. So this is the start time of the next activity. So each of the edges has a from and a to. So this is the next activity. Its start time has to be greater than or equal to the start time of the previous activity. So it's the from part of that edge, plus the from part of the edge is normal time. So this is sort of taking the normal time plus its start time of the previous activity has to finish before the next activity can start. Okay. And we get one constraint for each edge in the network. And then we can go ahead and solve it with ROI. And if we do that, we'll get a couple things out. So solution will give us the start times for each of the activities, which match up with what we sort of did on paper. But this is kind of a good check that we can start activity A right at the beginning. Interesting to note, right? Our variables, our start times, have a lower bound of 0, which prevent us from starting before 0. But because A has no predecessor, it sort of just gets pushed all the way to 0. We don't actually put any constraints on when A can start other than it has to start and finish before B and C can start. So we don't have to actually tell it start at 0. B and C start at time 2, D and E start at time 9, and F, that last activity, starts at time 17. It then takes 3 units of time. And so here's our objective value of 20, telling us that if we do everything normal time, it will take 20 units of time to complete the project. Okay, and then I've gone ahead and extracted the constraints here. And then I can take the constraints and multiply, do a matrix multiplication with the solution. And that will essentially give me how much slack there is in those constraints. And so I can take that amount of slack and put them with the edges, so that because each constraint in this case corresponded to an edge. And so it's maybe not 100% clear because, well, so anything with slack is not on the critical path. Now, I will say some of the things that do have slack are on the critical path, in that we said that B is not on the critical path. But the way this is set up, it's going to start B as soon as it can, even though it has some leeway on when it could start it. The maybe more important thing to note here is that from B to D has slack, which means that we know that B is not on the critical path, and B to E also has slack, so we know that B is not on the critical path. Okay, and so in sort of determining what's on or off the critical path, maybe more look at what nodes are on the from side have some slack. And so then we also see that D to F has slack, and so we know that D is not on the critical path. Okay. And so it's maybe not 100% clear just by looking at the slack what's on the critical path, but it's maybe more clear what's not on the critical path, and that edges from B to D, B to E, and D to F are definitely not on the critical path. And so you can kind of cut those ones and then look for paths that still exist from the start to the finish, and that those will be your critical paths. Okay. It really does help to maybe jot down some notes on the actual network to kind of figure out what that critical path is. And in this case, it's from A to C to E to F, A to C to E to F that's on the critical path. Okay. Now let's incorporate the ability to crash some of the activities throw more resources at them in order to speed it up. Our initial analysis tells us that we can complete the project in 20 weeks, but maybe we need the project done in 15 weeks. Can we cut 5 units of time off this activity? Well, you could just sort of repeat the analysis above with, instead of using the normal time, use the fully crashed time and see what is the minimum amount of time we could finish it in. In this case, looking at it, the minimum amount of time that it will take. Oops, I left off the time for activity A. Anyways, the minimum amount of time it takes ends up being less than 15. So 15 is achievable. If it wasn't achievable, our next step when we run the optimization would give us no feasible solutions. Okay. So here we're going to set up with a target project time of 15 weeks. Just sort of for reference, the normal cost total is going to be the sum of the normal cost nodes, just so that we have that for reference. Now, here's our PERT crash model. We're going to add variables for the start time. Those are the same. We're now going to add variables for the amount of time crashed. Okay. And so I named that crashed with an ED time. So that's the amount of time that activity was crashed. It's going to be a continuous variable with lower bound 0. We'll add the upper bounds in a little bit. Our objective, we're going to sum over the crash times the marginal cost for that node plus the normal cost for that node. Okay, notice the normal cost for the node doesn't get multiplied by any decision variables, and so it's essentially constant no matter what's going on in our problem. Okay, no matter how much we choose to crash, and so we could move that outside of the problem and just try to minimize the cost of crashing, and we'd get an equivalent solution just with having subtracted off the total normal cost. Okay. Now to incorporate the crash time into the time for task, the start time of the next activity has to be greater than the start time for the previous activity, plus the normal time minus the amount of time that we've crashed. Okay, and so this crash time essentially reduces the time for that task. Otherwise, that constraint is the same as before. We're going to want to add constraints that provide an upper bound on the amount of time that we've crashed. And so the crash time has to be less than or equal to that node's max crash. And we're going to have that for each of the nodes. And then we add one more constraint with our goal, which is that the total time is less than 15 weeks. And so the final activity in this case is activity F. And so start time for F plus normal time for F plus crash minus crash time for F has to be less than or equal to the project time. Now, this is the case when there's one final activity. If there were multiple final activities, you'd sort of have that all of those final activities are finished before that project time. And so you might have a couple of these final constraints if you wanted to. You could also create an extra activity that had no time itself, and sort of have a start time for that variable or that activity that sort of catches that, and just then constrain that to be less than or equal to the project time. Okay. And then that's essentially the formulation for the PERT model with crashing. And so let's go ahead and run that. We'll run it. We get the solution here. Let me just run through these parts one at a time. So the solution will give us our start times for each of the activities. So we're going to start A right at the beginning, B and C start at time 2, D and E start at time 7, and F starts at 13. So we're starting things a little bit earlier than we did previously. And then how much did we crash the activities? A and B are not crashed. Remember, B was not on the critical path, and so we shouldn't expect it to be crashed. D was not crashed either, but C, E, and F, which were all along the critical path, got crashed by 2 units, 2 units, and 1 unit. Okay. And so let's maybe look a little bit at the intuition of why those activities were crashed. So our total objective value here was a cost of 20.83 units of cost, whatever cost units these are in, whether they're thousands of dollars or what, depends on the context of the problem. Here I've gone ahead and created a sort of results data frame where I'm taking some of the stuff from the nodes, essentially the names of the nodes, the marginal cost, and the normal time. I'm adding in our start time, which were the first 1 through number of nodes of our variables. Our crash times, which are the rest of our variables, so from num nodes plus 1 to 2 times the num nodes, because we've got twice the number of nodes is the number of our variables. And then I've also recorded the finish time here, which is the start time plus the normal time minus the crash time. And so let me run these lines here and let's look at these PERT results. Okay, so for each of the activities, here's the marginal cost. And so one thing to note is that we're going to prioritize crashing activities that have the smaller marginal costs. Okay, so looking at this and are on the critical path. We're not going to crash things that are not on the critical path. And so in this case, activity C has the lowest marginal cost. And so we crash at 2 units. Interesting, and I didn't include it in this table, is that we could have crashed activity C more than 2 units, but the reason why we stopped crashing activity C at 2 units is that once we've got C down by 2 units to take essentially 5 units of time, then it finishes at the exact same time as B, right? Before, B finished at time 7 and C finished at time 9. And so really B had some slack in it. But now after crashing C by 2 units, they finish at the same time. And now B is actually on the critical path as well. And so if we wanted to reduce or start D and E any earlier, we'd have to crash actually both B and C at this point, because now they're both on the critical path that goes through D and E. Okay. D and E, we start at time 7. Their normal time is 6 and 8. We crash E by 2 units, and so then E's total time ends up being 6 units as well. And now D and E are actually finishing up both at time 13. Okay, and so they end up both being on that critical path. Finally, activity F starts at time 13. Its normal time is 3. We're only allowed to crash at 1 unit, and so we crash at that 1 unit and we get done in 15. And so looking at the nodes that we did crash, C was the cheapest per unit time, then E, then F. And we notice A was also on the critical path, but it had a marginal cost of 2. And so it was the most expensive of the activities that were on the critical path to crash. And so we didn't crash it. But we also sort of only crash up to the point until then there might be other critical paths. And so we didn't keep crashing C even though we didn't reach the max crash, because then we would have also sort of added on the cost of crashing B as well if we wanted to get D and E started any earlier. Okay, so I encourage you to sort of maybe find the linked example of the network and sort of think through kind of what's happening once we've reduced the times for each of these. Okay. We can yeah, look at the same slacks that we did before. And now we notice that there's no slack in any of those, and essentially all paths are now critical paths, in that we've the activities that were sort of at the same layer or stage in the overall process, but were taking longer, we crash those times so that they're now the same length as the task that was being done in parallel with it. And so that's sort of the rule of thumb or the conventional wisdom if you're sort of thinking of this without optimization, that if you have multiple activities that are in parallel, then you want to sort of reduce the longest one so that they're more similar in time. Okay. One thing I will note is that PERT CPM sort of assumes that these parallel activities have parallel sources of labor, and that if it's just one person doing it, usually you can't do a lot of these things in parallel. And so then you end up just with one long path of maybe activities that need to be done. So interesting activity. There'll be a homework problem where you'll get to practice these techniques, and you can modify the code from this example and use it on the homework activity. So that's it for this example.